Simple harmonic motion is the oscillatory or periodic motion of an object that moves under the influence of a restoring force. And a restoring force is any force that always pulls an object back towards equilibrium or the center of the motion. Some examples you might be familiar with from your regular life would be a child on a swing. The child swinging back and forth is in periodic motion. Got a couple of videos I can play for you. This is a mass on a spring, a simulation of a mass on a spring. If we pull it down, a spring force makes it oscillate up and down, back and forth above some center point. This is the kind of example that we'll cover most in our lectures. Okay, the other one we can look at, it's kind of nifty. We won't do anything this complicated, but it's fun to look at. This is not just one pendulum, it's a whole bunch of them with different lengths. So we see that each of those pendula, they do swing back and forth. What's kind of nifty is that they swing with a different period. It takes a different amount of time for one swing back and forth. That's because that time depends on how long it is. And when we're swinging them all together, we see that we get this pretty cool pattern emerge. Okay, even though we're not going to analyze something like that, it is still pretty fun to watch. Let's use Newton's second law to find the equation of motion, so that's the equation for position as a function of time, for a mass on a spring on a horizontal smooth surface. So I've got a simulated video here. I'll hit play, there we go. So what we do is we take the mass, we pull it some distance, and then we let it go. Where it starts, that's the equilibrium point. There's no force there. And then we pull it to the right and we release it. When it's to the right, the spring force pulls it left. When it's to the left of equilibrium, the spring force pushes or pulls it to the right. It's going to oscillate back and forth forever because there's no friction with a repetitive motion or periodic motion. Okay, let's get some symbols and some numbers and some definitions down here. The line that goes through the middle, that's called the equilibrium. That's the place where there's no net force. So this position we would normally call x equals 0, and that's the equilibrium position. Then we take our mass and we pull it out some new distance. So we pull it out to here. Our new position we can call x, and we know that the spring is going to exert a force on the mass that pulls it to the left. So there's the spring force on the mass. What we know about the spring force is that it has a magnitude of kx, that's from Hooke's law, and we know that the force points left, so it's going to be a negative force. Okay, let's get this stuff in Newton's second law. Newton's second law says that the sum of the forces acting on our mass is mass times acceleration. In the x direction, the only force we have is the spring force. It's to the left, so it's negative, and it has a magnitude of kx. So that's equal to m times a. Right here is a good place for a couple of definitions. K is our spring constant. It has units of newtons per meter. M is the mass of our oscillating object. Typically that would have units of kilograms. Okay, so we have mass times acceleration equals minus k times x. That means acceleration is minus k over m times x. I divided both sides by m there. We remember that acceleration is the derivative of velocity, but velocity is the derivative of position. That means that acceleration is the second derivative of position with respect to time. Okay, so you have to do the derivative of position twice to get acceleration. So that's equal to minus k over m times x. Now this is an equation. You'll probably learn how to solve this equation at some point in your math career. This equation has a solution that x as a function of time, the brackets means that x depends on t, it doesn't mean x times t, is equal to some maximum value, we call that a for amplitude, times a cosine, so the cosine is the repetitive or the periodic part, root k over m times time t. If you wish, you can go ahead and try plugging this in for x in the equation. So you can pop in your a cosine root k over m times t for x. Then you can take the second derivative of your x equation and plug it in on the left-hand side. You'll see that those two sides will be equal to each other. So you can see that that equation, that is the solution to that equation. A typical example we study is a mass bouncing up and down on a vertical spring. So I grabbed that and I set it up in the lab, and what I did was I used a motion sensor and some lab equipment to plot some graphs. So let's have a look at the graphs and then we'll talk about those a little bit.
So we have a small mass here attached to a spring. We know that when I push this mass down, it moves up and down. Now what we want to do is we want to plot that motion. What does it look like, the position as a function of time? So I have on my computer screen here, the top graph shows position, the middle graph shows velocity, and the bottom graph shows acceleration. I'm going to measure those values using a motion detector. So I'm going to place this motion sensor under the mass, then I'm going to hit collect and get a set of data. So I've got my mass moving up and down in the simple harmonic motion. I'll hit collect and let's watch those graphs come up. They look a little funny right now. I'm going to hit auto scale. And we see that the position, velocity, and acceleration, all of those graphs seem to be represented by a sinusoid. They move up and down about some center point. So this is certainly periodic motion, and it also looks like simple harmonic motion.
So we used a Newton's second law analysis to find that the position as a function of time of a simple harmonic oscillator is some maximum value a times cosine root k over m times t. And then we set it up and we looked at it experimentally, and we also saw a cosine value. So let's get to work on our definitions. A here is equal to the maximum possible value of x. So maximum value of x. It would have the same units as x. So if x were in centimeters, a is centimeters, x is meters, a is meters, and so on. The name of that is called the amplitude. Okay, let's look at our graph a little bit more closely and see what our graph tells us. So x goes up and down between some maximum and minimum values. So it goes between plus a and minus a. And it takes some amount of time. So it starts at a. Some amount of time later, it's back at a. This amount of time is called the period, and that has a symbol of t. So that amount of time is t. T equals the period, and a period is the amount of time for the oscillator to return to its same position. So we indicated one value of t, but a t might also be from a trough to a trough, the two lowest points. Okay, so if our graph repeats, if our position graph repeats over some time period, that graph could also be represented as x of t equals a times cosine 2 pi over t times time t, because that also represents a repeating cosine graph. So now we have two equations. We have x of t equals a cosine root k over m times time t. And for the same oscillation, we have x of t equals a cosine 2 pi over period times time. These two equations describe the same oscillation. So x is the same for both, a is the same for both, time t is the same for both. So our conclusion then must be that root k over m must be equal to 2 pi over period t. And that value is called the angular frequency or the angular velocity. That has a symbol of the Greek letter omega, that's like a curly W, and it has units of radians per second or seconds to the -1. Either is acceptable. So here's a quick summary of what we have so far. X is the amplitude times cosine of the angular frequency times time t. Omega is 2 pi over the period, or the square root of the spring constant divided by the mass. One thing that's pretty important about this equation is the starting point. See in our graph here that x begins at the amplitude, and our equation is x equals a cosine omega t. This equation is true when the oscillator begins at the amplitude. So this is for oscillation which begins with x of 0 equals amplitude. Okay, so we've got this description. It is important to ask though, what if it doesn't begin at the amplitude? How do we deal with that? So let's see how we can use our equation to describe motion that doesn't begin with the amplitude. So when it does begin at the amplitude, x of t is amplitude a times cosine omega t. If you ask what is x at t equals 0, you would see that x of 0 equals a times cosine of omega times 0 equals a times cosine of 0. Cosine of 0 is just 1 equals the amplitude. Okay, that matches what our graph shows us. X at t equals 0 is equal to the amplitude. So if the motion does not begin at the amplitude, x of 0 is not equal to the amplitude. To arrange for this in our equation, to accommodate this, we say x of t is equal to a times cosine of omega t plus some number. And that number has a symbol of phi, and it's called the phase constant. It's in radians, and it allows for a different starting point. So let's try that out in our equation. What is x at t equals 0? So x at t equals 0 is equal to a times cosine of omega times 0 plus phi equals a times cosine of some number phi. Now, what we know about cosine of a number is that it will always be less than 1. So this tells us that x of 0 is a times some number that's less than 1. So x of 0 is less than the amplitude. That matches the graph. So our starting point on our graph is some number that's less than the amplitude. So our general expression, or our general equation for position as a function of time of any oscillator that can have any starting point, is x of t equals a times cosine omega t plus phi. So anytime you have to write an equation of motion, this is what that means. It's the equation for x that gives the amplitude, the angular frequency, and the phase constant. Let's use our equation for position now to find our equations for velocity and acceleration. So our equation for position is x equals a times cosine omega t plus phi. X oscillates back and forth between the plus amplitude and the minus amplitude. One thing important here is omega is in radians per second. Phi is in radians. This tells us that our calculator has to be in radians mode. That should hopefully help you avoid a few calculator errors, which are really common. Okay, let's get to our velocity equation. We know that velocity as a function of time is the derivative with respect to time of the position equation. So we're doing d by dt of a cosine omega t plus phi. A is a constant that can come out front, so then we've got the derivative of cosine omega t plus phi. The derivative of cosine is minus sine. And then we also have to multiply by the time derivative of the argument. The derivative of omega t plus phi is just omega. So our equation for velocity of the oscillator is minus a omega sine omega t plus phi. Now, velocity also has a maximum and minimum value. That, of course, will be different than the position's max and min because they're not the same thing. They even have different units. If we want to find the maximum, we have to think about the fact that the velocity goes as a sine function. So our velocity will be a maximum when our sine function, okay, let's see if we can figure this out. Sine of any angle can always vary between +1 and -1. The biggest sine can never be is 1. The smallest sine can never be is -1. So to get a maximum velocity, sine is either going to be +1 or -1. Now, because velocity goes as negative sine, to get the biggest possible value for our velocity, we're going to have our sine term equal to -1. So that gives us that V maximum equals minus a omega times sine. We said that that was going to be equal to -1. So V maximum is equal to a times omega. Let's label that on the graph. And the minimum is minus a omega. Okay, let's do our acceleration next. I think I have enough room. I'm going to give it a try anyway. So our acceleration is the derivative of velocity with respect to time. So acceleration is d by dt of velocity with respect to time equals d by dt of minus a omega sine omega t plus phi. Okay, I can take my minus omega t out front, minus a omega out front because it's constants, d by dt sine omega t plus phi. The derivative of sine is cosine. Then I have to multiply by the derivative of the argument, which is just omega. So I get a of t is minus a omega squared times cosine omega t plus phi. There's our equation for acceleration. If I want to get my maximum acceleration, a is going to be a maximum when my cosine term is equal to -1. So then a maximum is going to be a times omega squared times -1 equals a omega squared. So those are my maximum and minimum values of my acceleration. If you look at the graph and you compare acceleration and position, you might see that those are flipped compared to each other. So that's something we might notice, and let's just do a summary of that on the next slide. Let's just take a quick look at that relationship between position and acceleration. Our acceleration equation is a of t equals minus amplitude times omega squared times cosine omega t plus phi. I'm going to rearrange that a tiny bit to say minus omega squared times a times cosine omega t plus phi. Now if I put brackets around this part, you might recognize this as x. So that means that our acceleration then is minus omega squared times x of t. That can be a useful relationship. So where we have a minus sign here, it tells us that x and a are exactly opposite. they're at a phase by pi. Okay, so they're exactly opposite of each other. They're shifted by a half of a cycle.